Welcome to the Neural Implant Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Laden Yurachek.
Hello, everyone, and welcome to the Neural Implant Podcast. Today's guest is Dr. Bradley Gregor of ASU, Arizona State University. He's the Associate Professor in Neural Engineering, Neuroscience, and Clinical Neurophysiology. His interest is mainly in restoring vision to blind people. So Dr. Gregor works with the company Second Sight in order to help restore vision to blind people by basically implanting a neural stimulator inside the eye in order to be able to send those signals to the brain. So in this episode, we talk about some of the challenges, some of the limitations, and maybe some of the new technologies, what's going to be coming out that's going to be able to alleviate and improve this technology as well. It's a very good episode, and we'll talk more on the other side.
I actually started out as a philosophy major and then got into philosophy of mind, and that led me to taking some neurophysiology class, and that was where I really got engaged, just really wanted to understand how the brain worked. Can remember very vividly reading Oliver Sacks' book. It's called The Man Who Mistook His Wife for a Hat, which is a great book about kind of some of the things that can go wrong at the high level in the brain, but from a more scientific, more medical point of view, how can we kind of address these really fascinating issues of what the brain does, but from a very rigorous scientific point of view, not a purely philosophical point of view.
Okay, and that interested you enough to, ditch philosophy and go into the field of neuroscience?
Pretty much that, and that there's no jobs in philosophy.
There's no philosophy factories, I guess, right?
Not getting a job as a philosopher is tough. But I really was mostly intrigued. I wanted answers. I wanted something more definitive, more concrete. And that's what really led me into this road now, where we're kind of trying to use devices and sophisticated technology to both understand the brain and then help treat different pathologies of the brain.
Yeah. So how did this start? I mean, you've been active for the better part of a decade or more than a decade, right? So yeah, how did this start? And did you immediately think to go into neural implants, or what was kind of the genesis of this?
Well, a lot of that was a bit of coincidence and luck. There's always some interest there. The real, I think, turning point in terms of getting into the neural implant, neural interface side of things was during my postdoc, which I did with Richard Anderson at Caltech. I just happened to be in his lab at the time where he was delving into these kind of cognitive level neural interfaces. And I just happened to be in the lab and got to help out with that project and learned a whole lot of stuff. I just really became fascinated with this idea of kind of tapping directly into the brain and really seeing if we could access information from even fairly high levels of the brain to allow control of external devices.
Oh, wow. So what were you guys doing over there?
Well, it was really basically putting microelectrodes into the parietal cortex of non-human primates and getting them to control a computer task, a very simple game. I think of it on a computer. And it was just basically really decoding the direction the monkey was thinking about moving its arm. But we would just do that before it actually moved the arm, and it could perform this simple task just based upon its thoughts and actually its arm movements.
So it was able to, the computer was able to predict where it was going to move its arm before the monkey knew where it was going to move its arm, something like this?
Well, the monkey knew what it was going to do. It just the task was a delay task. So basically, we'd get an instruction to move in a particular direction, and then it would have to wait for a little while. We'd actually have it, just hold its position, and then it would get a cue to move its arm to reach and touch a particular location, and then that was how it got its reward. So we trained to do that, but then we'd turn the decode on and just decode what was being processed in this high level processing area of the brain during that wait period, and then reward it based upon if it thought about making the right movement. It could actually think about moving now a computer cursor rather than its actual arm to the location it was supposed to. And we would just do that during that wait period.
Interesting. So the way you've described it, it kind of sounds almost like the brain almost like loaded a spring or something like this. It's like it's prepared this like pathway and what it has to do, and then at the right time it just says, okay, fire, like letting go of the spring, and it just the rest does itself. Is that kind of accurate or not?
I think so, yes. And this is stuff that goes back to Richard Anderson's work. He spent many years really just working out this parietal cortex, the areas of it, what it encodes, how it processes information. And one of the fundamental findings is that it holds on to motor plans. It seems to be involved in thinking, okay, I'm going to do something in the future. I want to plan for that. I want to prepare for it. And then somehow when you decide to move, it actually transfers that into the more motor cortical areas that then execute the plan. And so it really was kind of this higher level, almost you could think of quasi-cognitive level sort of process that's going on. And that's what we were trying to decode.
Interesting. Okay, so you were there for your postdoc, right? And then what was your next step? And what have you done since then? I guess. I mean, this was like in the late '90s and early 2000s, right? So you've done a lot of work since then, right?
Yes, absolutely. Well, I hope so. Yeah, that was all Richard's stuff. I mean, he's been thinking about this stuff for decades before I even got into his lab. And so that was, kind of this decoding of intention was something he'd been doing and other labs been thinking about. And I really wanted to kind of do a little bit of a different approach and really think about maybe sensory restoration. And so I got involved with kind of doing this research on stimulating the visual system to try and get people who suffer from blindness to have some level of restored vision. And so I spent the next several years when I was at University of Utah, again, just doing studies in non-human primates and directly stimulating the visual cortex to see what kind of vision we could provide to them.
Oh wow, that's really interesting. Yeah, we actually had a guest on, Jens Naumann, and he was the first patient to be implanted with a visual implant of a visual prosthesis. He was able to see like 13 pixels or voxels, and was actually able to drive a car with this. Is this something what you're doing? And I mean, isn't this like a whole order of magnitude or even a few orders of magnitude more difficult because it's just so much more data that has to go through, right?
Well, it's so two things. So Jan Newman's, his book, he's wrote a book on his experiences called In Search of Paradise, I think, which is a great account of his experiences. And yes, we're very much trying to do that sort of work using a little bit different technology. It is, I wouldn't say it's harder than the decoding side of things. It's harder in one sense that, we're putting electrodes in this just incredibly sophisticated and complex bit of tissue. And I don't think it's, an exaggeration to say that the human cerebral cortex may be the most complex chunk of matter in the known universe. It's just so hyper complicated. And then, we come along, we put these electrodes in it and just put in current and expect reasonable things to happen. And kind of remarkably, it does. We can get people to see phosphines as little points of light. So you can think of it as like a pixel or a voxel on a screen. And that gives them some basic limited vision. And for somebody who is completely blind, that's a serious change. That's a real impact on their life.
Yeah. Yeah, absolutely. I mean, it goes from, not being able to drive a car, not being allowed near a car, and then being able to drive a car, albeit, in a parking lot, but still.
Yeah. Well, and I would be somewhat cautious about driving the car sort of thing. I'm not sure that he guided the car in a parking lot under very controlled circumstances. I would be very scared if he was out on the road. But for somebody who is profoundly blind and just trying to walk around in an unfamiliar room, and if you can see that, there's something here, there's a piece of furniture here, or there's a doorway over here, it just really helps you kind of navigate and orient for objects that are at distance. For close objects, they can often they have a cane or they can use tactile input, and that will help. But it's those things that are at a distance and that are moving. I think trying to walk around in the streets of just your town and trying to cross the street. I mean, how can you really know if there's a car coming or not? And do you have confidence that everybody's really going to stop for that stopwalk, that crosswalk? But with the type of devices that are coming online now for people in the retina, and we're hoping to take to the cortex soon, you could literally get a sense, okay, there's a big object coming towards me, so I shouldn't step into this street right now.
Wow. So what inspired you to actually go down this road? Did you have some family members or friends that were blind?
No, it really was a little bit of just happenstance. I mean, a lot of my life has just been fortuitous luck. I mean, just been, the hand of God sort of thing. Getting to work for Richard was really a big step, and just learning about this sort of technology and how to think about these sorts of problems. And then when I went to Utah, the University of Utah has a long history in working in visual prosthetics. And so I got to work there with Dick Norman and some other folks who have been thinking about these sorts of applications for many years. And then kind of looking now to take that in a little bit different direction just because of the technology. I think there's maybe some simpler approaches that will get quite good results, but with simpler technology.
Ooh, interesting. I'm curious. Tell me more.
Well, so the real kind of recent bit of fortuitous luck for me has been starting to work with a company called Second Sight. They make currently a retinal prosthesis. So for people who suffer from retinitis pigmentosa, they go in and can implant their device in the eye itself and directly stimulate the retina and restore limited vision. And it's been quite successful. They've done, I believe, several hundred patients in Europe, and they're starting trials here in America now. And it works. It's pretty an amazing piece of technology. What I've been doing with them is then asking the question, can we take that same kind of technological platform and go to the cortex and really restore the same level of vision or something better? And that would allow them to help patients who don't have a functional retina. Because for currently what they're doing right now, if your retina itself is completely non-functional, then their device can't help.
Interesting. So it uses the existing retina and it sends it. It's kind of like a cochlear implant in this case, right?
It's very similar to the cochlear implant. You can think of it kind of like a two-dimensional cochlear implant because it's a grid of electrodes. And for the patients who have the rods and cones, kind of the photoreceptors of the eye are degrading or malfunctioning, they can't see because of that. But then the ganglion cells, the cells that send the electrical impulses back into the brain, are still viable, then their device works. But if the retina is so damaged that there's literally no connection in the case of trauma or something like that, or the ganglion cells themselves are destroyed, then you have to do something more in the visual processing stream to help correct that, because the retina is just not there.
Is there a problem with atrophy of the cells? I mean, after certain years of use, maybe they go away. It's do you have to catch it within a few months of becoming blind or something?
This is a great question, and this is an open question still. There's certainly a ton of plasticity and development in the visual system as a small child. So you have vision, you get this visual input, and that sets up much of the higher cortical structures that then process vision. And so if you've been blind from birth, there's kind of this concern that, the parts of the brain that process vision may have been, co-opted for other functions, or their architecture will be different because they didn't have that input. And so that leads to the question of, would a device really work there? So for people who have been blind from birth, this approach may have some other challenges. Now, somebody who just grew up and was normally sighted but then lost vision, there's at least a reasonable understanding of how vision is processed in these early visual areas, so that we can go in and do this sort of interface and have good confidence that it'll work. There's probably some plasticity that occurs after you lose sight, but that's probably kind of more of the shaping plasticity, not changing the fundamental architecture and connectivity of the brain. So the thinking is that it should be fine for even somebody who's been blind for a long period of time, as long as they did have sight at some period in their life.
Yeah, I've heard about this. Like people who get their sight back. I mean, they could be looking at a stapler, for example, and I mean, they see the stapler, but they don't really know what it is until they like come and pick it up and like feel it, and then they're like, oh, that's a stapler. Just because, like you said, the neural architecture is not there, and it wasn't really developed as a child.
Yeah, but there's typically for the type of patients we're talking about, there's their eye has been damaged, or there has been so damaged that there's not a way to restore natural sight. But there are conditions where people have had like severe cataracts or other sorts of visual impairments that got corrected, and so sort of the natural visual system got restored. And in some cases, they actually don't like it. They find that input to be disconcerting in some way because they didn't grow up and it didn't kind of come into being naturally. It didn't have that chance to set up the architecture. And so it's kind of a strange input. And so it's one of those things to be very thoughtful about when we're talking about these sorts of interventions for people.
Yeah, it could be like you're trying to help somebody, and in the end, they don't like the help because it's annoying, or it's like, it's very, I don't know, how would you say, like noisy or something like this, right?
Exactly. Well, and you talked about Jans Newman, and that work came out of the Brindley and Dobell's work back in the 60s and 70s, where they really first stimulated the human visual cortex and showed that you could get people to see spots of light. But in those early patients, they all really didn't like it. It was very bright, very glaring, very intrusive, mostly because they were working with 1960s and 70s technology. And so there was not kind of the nuanced electrical systems that we have today. And so there's a real possibility, if it's not done well, it is actually something that's the patients don't like it, they don't want it.
Yeah, exactly. Using their rotary telephones and bell bottoms, to get the job done.
Yeah, exactly. If you look at some of the pictures of the technology they're using, you're just amazed with what they got done.
Yeah, I think it'll be the same way in like, what was that, 60s? So that'll be 50 years from now. They'll be like, oh my God, they were using this.
Yes, I'm hoping I'll be around long enough to hear my students mock me and the technology I was using.
Interesting. So would you say this is one of the bigger challenges, is like making it less annoying or less intrusive for the patients, or what is the biggest challenge in this work?
Well, no, so I think that now really just because of increased knowledge and kind of the exponential increase in technology, the ability to manufacture really precise and very small electrodes and having electronics that can control it and do the stimulation with great precision, it's really not a question of comfort or acceptance by the patients. It's really the big question is how much information can we give them? How much visual input can we provide? And that's really where we're trying to push it now. It's just to maximize that. Right now, the retinal implant that Second Sight does, I think it's 48 electrodes. So you can really think of like a 48 pixel screen. So it's not, high def or anything like that. But it still changes their lives. It really has a significant impact on their lives. But it would just be exciting to provide, hundreds or maybe even thousands of pixels using lots of electrodes in a very sophisticated way to provide more naturalistic vision.
Yeah, definitely. I mean, 48 is more or less 7 by 7, so you could see kind of what's going on a little bit. But yeah, I mean, it wouldn't be high def at all, like you say.
No, it really is just to help with activities of daily living and getting around in unknown environments and that sort of thing. But you think if we could get that up to where it's, maybe, thousands of pixels, you could take the vision to a place where they could really start doing that more kind of detailed object recognition. And the dream would be kind of facial recognition and even facial expression recognition, because that's such a intimate part of human communication is, what is the expression on the person's face as they're talking to you. It's not just the words, but it's, what they're doing, their gestures, their expressions all really matter.
Yeah, exactly. That could be maybe one of the most important things. So what's stopping you guys from increasing the resolution? Is it the electronics are too big? Is the equivalent of a rotary telephone still happening with you guys, or what?
No, honestly, I'm going to say this somewhat jokingly. It's just money. We need more money. So
Please send money.
send money and we'll get this done. Because most of the technology is in place. There are some technological challenge, but a lot of those have really been solved. I mean, as a society, we are great with electronics and hardware. We've got these fabulous devices in place. But what we really need to work out is kind of the biological side of things. How do we design the actual grid that touches this, the human cerebral cortex? How do we make that shaped and compliant that it, fits with the brain and maybe even to this specific patient? How do we get the number of electrodes high enough to provide the kind of vision we want? And then really that would allow us to go after, higher level, higher kind of quality vision, and maybe start looking into the kind of the more subtleties of vision, what we take for granted, like color vision and texture. It would just let us do more sophisticated things. And to do that, we're operating in some unknowns, is that we don't necessarily have a deep understanding of how the visual system does that. And then so we have to work out how to do the stimulation properly, and are there sophisticated ways to do that? And these are kind of open scientific questions that are very approachable. It's just going to take time and effort.
And money. So how big is the check that they should send?
How much you got?
$43?
Yeah, in my wallet, I got about $20 right now, I think. There's a ton that could be done with little bits of money. It really depends on, if we're talking about trying to take something where it's a fully human-approved system with thousands of electrodes and it's going to have color vision. But now you're talking about a very deep, long, ongoing research project, because there are some scientific unknowns there. You're talking about a significant increase in the technology. You're talking millions of dollars. To do something, much more tractable, and just to try and get something that's going to significantly increase patients' quality of life, something like just scaling up to have larger electrodes and maybe bigger field of view sort of thing. I mean, that's the kind of thing that can be done pretty reasonably on typical grant-sized budgets.
And another question, are these implants like visible? Like if you see somebody with this, could you tell that they have it implanted?
Only because of the external equipment. So the only device that I know of that is like really commercially available is the second sight device. And it is very similar to the cochlear implant, where it's the actual stimulating electrodes, and the device itself is all completely implanted in the eye. So you would not know it was there at all. I mean, shower, bathe, swim, do whatever you want with the device in. And there's a wireless connection then between that device and a pair of glasses that you wear, and the glasses contain the video camera that transmits the video signal into the kind of the processor there, and then to the stimulating device. And there's a belt pack that goes along with that. So if you're wearing the external parts of the device, you can kind of tell it would look like somebody's wearing kind of a funny pair of sunglasses with a very large Walkman music player thing. But if you can take that off, and then you couldn't tell at all.
I think I saw something recently that Google developed some kind of contact lens that was a camera. Would that be possible to integrate into this?
Well, and this is where things get pretty exciting from a technological point of view. There's a lot of work being done to do miniaturized stimulators that go in the eye and coupling them directly to cameras. And this would be some fascinating stuff to just have in terms of helping people. And it also would help work out some of the issues with the visual system that are unique. And people don't think about this a lot. But it's the movements of the eye are as important to vision as the actual receiving the light. And the brain does a lot of very sophisticated image stabilization and compensation for movements that are just built deeply into the visual system and the control of the eyes, the head. And when we start stimulating the cortex directly, we kind of bypass that system a little bit, and we're not really tapping into our utilizing the eye movements and head movements to guide the image. And so when you start talking about a contact lens that's on the eye for acquiring your image, all of a sudden you've brought back in a lot of those systems that are in the brain that help vision just, endogenously. And that would be really exciting thing.
I think the eye like constantly vibrates actually, and that actually kind of brings things in focus, and you're able to see better because of that. But that would also suggest that you have to have like a very high frequency, a very low latency as well. What kind of speeds are we talking about?
Yeah, no, you're exactly right. Your eyes are almost constantly in motion. You're always making little microsaccades, and it's just to constantly shift the light that's hitting your retina a little bit each time. It just kind of gives more information. It helps define edges and all sorts of things. And that's happening on kind of the millisecond time scale. Everything in the brain kind of happens on the millisecond time scale. So, you need to be able to acquire those images, process them, and then address the stimulation all on that sort of time scale. Fortunately, electronic speeds are usually on the pico nanosecond time scale. They're crazy fast. Electronics are super fast. Where you really kind of get into a bottleneck with time is when you do the stimulation of the neural tissue. You can't do that too rapidly because you can have this phenomenon where you get too much charge accumulated in the tissue, which can damage the tissue. So you have to think about the interface of the electrode to the tissue, and when you start pushing charge through that interface, how fast can you do that? And it can be done on the tens of millisecond time scale. But when you start really thinking about these super fast processes, you do have to pay attention. But the bottleneck is on the biology, not on the electronics.
Interesting. So what would be the solution to this? I mean, I know, for example, in traditional microelectronics processors and everything like this, the reason that the processor speed increased so dramatically is because they were able to actually shrink the size of the wires, the leads, and transistors and everything like this. And so there was less charging time and everything like this. Would something like this be possible for the implants as well? Like if they're smaller, would there be less of an issue with this, or maybe like a better conducting material, or what would be the solution?
Well, you've really hit on something that's near and dear to my heart, because literally for like the past 10 years, I've been beating the drum that we need to make the electrodes that do this smaller. Back in the 60s and 70s, they were literally using electrodes that were like centimeters in diameter, so they were huge. And if you think of just the scale of the brain and of a neuron and kind of the scale it operates, it's on the micron level, so we're orders of magnitude off there. With the current technology and what we're doing right now, we're using microelectrodes, so electrodes that are smaller than a millimeter in diameter, so quite small. But even with an electrode that's small, we're stimulating a fairly large chunk of the cortex every time we do a stimulation on one of those electrodes, and probably on the scale of a millimeter or so, which is a lot of neurons to activate all at the same time, or some population has been activated at the same time. The ideal situation would be able to address neurons individually and say, I want this neuron to fire an X1 at X potential now, or an electrical discharge now, and then in the next millisecond have its neighbor fire a discharge. That's currently beyond technology, I would say. The optogenetic stuff is closest to that as I think we have. But there's lots of work to be done to work out many other issues that go along with that technology for this visual prosthesis stuff, at least.
Yeah, interesting. Yeah, I talked to Ed Boyden, who developed the optogenetic technology. How would you integrate that if it would be possible? Would it be possible to integrate this technology into it?
Absolutely, and then I think that is happening. The optogenetic technology is awesome. It's just opened up a whole world of research and just technological capabilities. The challenges are going to be kind of on the neural interface side of there. The optogenetics lets you get down to kind of that cellular level, that neuron by neuron addressing. But then to interact with that neuron, you're using light. And now you've got this problem where you have to then have an interface that can send out little tiny pulses of light with the proper focus and all that sort of thing. So it's a similar problem, but now rather than the bottleneck being kind of tissue and electricity, it's light diffusion and tissue. And so there's some really neat stuff being done there with different wavelengths of light, and it's going to be fascinating to watch that technology develop. I really want to do things for myself personally, just that I have a little bit shorter time horizon because I'd like to see them help people before I die. And that's maybe just me being a little selfish, but I don't want to delay my gratification that much. I want to see something good come out of this while I'm still here. And so we're focusing more on the electronic and just direct electrical stimulation side. And there's, I think great potential there too.
Okay. So maybe the less quality achievement, but something nonetheless in a shorter time scale rather than the I don't know, Hail Mary or something like this that could take 20 years, right?
Yeah, and the optogenetics, great things are going to come out of that, and it's going to be really cool. With the microelectrodes, we kind of know what the problems are and how to address them. So I know it's just time and effort to get it to this place where we can do better. And really, it's all about changing people's lives. It's just, can we deliver significantly improved vision over what they have right now that it impacts what they can do. And this is what really motivates me. If we can get to a point where we've got a device that has the properly designed and laid out electrodes that let people recognize their children and interact with their children and have get the emotional content of facial expressions, that's the kind of thing that I just feel my life was worthwhile. I've done something good. And so that's what I'm aiming for.
Do you have any recommendations on who we should talk to or what we should read?
Well, boy, honestly, a great read is Jan Neumann's book that just walks through what was done in, I think, most of the 90s with this sort of technology. It's come a long way since then, but it's a very human story. It really kind of talks about how it impacted his life and how things kind of went wrong some ways and how they could have been done better. But yet there's the hope there. And I think we're really starting to see now a lot of that early work pay off and translate into devices that you're going to start seeing much more commonly. Where you're going to see these sort of micro electrode arrays that are just interfacing with the brain and stimulating with complex patterns, but small levels of current. And you're going to see that for vision. I think you'll start seeing it for, sensor feedback for prosthetic limbs. And there's even the potential for starting to see this sort of technology being used for treating kind of even more fundamental pathologies like Parkinson's disease, and even maybe some hope on kind of more the psychiatric pathologies where people are fighting with severe depression and things like that, where there's not great treatments and a lot of suffering that could really be alleviated.
Yeah, he was quite, I guess, upset that it was 15 years since basically his implant, and pretty much there has not really been any significant breakthroughs in this very, very long time. And in the electronics world, this is an extremely long time.
Well, and he's justifiably frustrated. I mean, I feel the same way, so I don't want to get too worked up about it. But because it's there. I mean, we know we can do it. We know it fundamentally works. There's economic forces at work. There are political forces at work. There's regulatory forces at work. It's just a lot of different battles that have to be fought to get it to where is it a place where somebody can just buy it and use it. And this is where I'm so excited to be working with a company like Second Sight, who really already kind of has it to that point now, at least for the retinal application, and we're just really hoping to extend it to a cortical application, which would be more applicable for someone like Mr. Neumann. And it would also address a lot of people who suffer from blindness across multiple causes of blindness. But we really have to prove that we can provide sufficient enough restoration of vision that it justifies it. And I think we are really quite close to that now. And it's just a question of some time and some effort.
This is so many different fields, and as you said, politics, regulatory rules, and all this. It's really it's kind of amazing that it has gotten so far, I guess. But many people are just starting out in this field, and I've gotten lots of listener feedback saying, "Hey, I'm a master's student or I'm a PhD student. What is your recommendation for them for how to get involved in this?"
Okay, this is something right in my alley here. So for somebody who's really thinking about pursuing this, get your master's degree, get your PhD. The The problem is you really have to be kind of a master of several different fields. You have to have a deep understanding of neuroscience, particularly visual neuroscience, or if you want to take this type of technology and apply it to another sensory modality, they need to become an expert in that sensory modality, be it touch, hearing, whatever. They need to understand, sufficiently the electrical engineering that goes behind these sorts of devices, how these circuits work. They need to understand, and I think this is perhaps the place where we have the least understanding, is really how charge and electrical stimulation of cortical tissue work, what that does. And there's a lot of interesting science to be learned there and some really good engineering to be done there. They also really have to learn a little bit about these regulatory environments, how you work with the FDA, how you can do clinical trials. Many of these problems can really only be addressed in working with human patients. And if you're going to do that sort of work, you have to obey a lot of laws and a lot of regulations. So you need to be versed in those as well.
Wow. Yeah, sounds complicated. Are you saying that if you don't have like a master's or a PhD or something like this, you really wouldn't be able to participate in this field?
It would be challenging, and it depends on what level of participation. If you have a bachelor's degree in electrical engineering and you want to be part of this, you absolutely can be involved. And I think there'd be many people in many labs and many companies around the country who'd be very interested in talking to you. But you're going to be kind of limited to just doing like the electrical circuit design part of it. If you wanted to really approach it from a higher level where you want to think about, okay, the problem is, people are suffering from blindness. What do I do to help fix that? And you want to maybe take some new approaches and you start thinking about, okay, I need to understand maybe optogenetics and how different wavelengths of light will interact with maybe different of the receptors that are generated through the optogenetics, and then can I increase visual information that way? And you can start seeing how lots of different expertise is required to start going after those sorts of problems. And you have to be versed enough in all the expertise to at least communicate with other experts. And you'll probably have like a primary one that's yours, but you got to have a kind of a breadth of knowledge that lets you communicate with a lot of different people. Yeah,
that definitely sounds like you need a lot of knowledge. And what about those people that don't have access to an amazing lab? Like you and I both came from University of Utah. There's a lot of work with neural implants in there. Now you're at ASU. There seems to be a lot of activity there. What if you're? I think I got a mail from Lithuania. What if you're in Lithuania?
Yeah. So one of the great things about just being at a place like ASU, it's a huge institution with massive resources and a long history of neural engineering. So yeah, most of the time I find if there's something I need, I just have to find out where it is. It already exists, so my problem's already solved. If you're at a place where you don't have access to huge amounts of technology in terms of device building stuff, one of the other things that you can always think about is trying to understand patient need. Talk to the people who are suffering from blindness. Really get a handle on what their daily lives are like, and what sort of tools or instrumentation or even just strategies and behaviors you could start thinking about to improve their quality of life. And this is something that often is missed at the big university institutions, is people just haven't spent time with the people they're trying to help. And so getting out there and getting exposure to people is hugely important. As is also the clinical components. I'm in an engineering school, so we tend to really focus on the device, the design, and all the engineering stuff. But communicating with your partners in the clinical realm who are going to do your surgery or apply your treatment, you really need to understand their world and how it operates as well.
Not forget the human connection. I guess as engineers and scientists, that's very easy, but remember that there's humans behind it as well.
Absolutely. And humans are complicated and they're messy and they cause problems all the time just because of who they are, not intentionally. But everybody's lives are so complex and different. So you think, you can't treat patient A exactly the same way as you treat patient B, even though you'd like to. You have to kind of understand how it all works together. And that involves not only patients, but the clinicians and the engineers. And it's a big team effort, but with lots of people communicating well, you can do amazing, amazing things.
Exactly. Well, this has been excellent, Dr. Gregor. Is there anything that you want to add that we didn't cover?
No, I think we hit pretty well. Certainly, I think this prosthetic technology, we're going to be seeing more and more of it, and I think it'll get to the point where you're going to start seeing it just on the street, kind of commonplace. There's always, currently there's the cochlear implant stuff you mentioned. And so I think we're just going to start seeing that for vision and touch. We're going to start seeing, very sophisticated prosthetic devices for restoring movement, restoring sensation. And I think that the other thing that we didn't talk about too much is kind of the social impact of that. I think it's important that, people, try and understand and not stigmatize that in any way. I think there's still, unfortunately, a little bit of social stigma that goes along with even somebody, being blind or being deaf, and that they have a cochlear implant. And I think it's just like, I think of it as anything else. It's just like, it's like I have high blood pressure, so I take high blood pressure medication. It doesn't bother me, but nobody can see it, right? So it's like no big deal. But if you have a prosthetic arm, people do kind of see that as something different, and it kind of draws social attention that I'm hoping people will just get over, because it'll become kind of commonplace, and so people just won't notice it, and it's no big deal. But those are the kind of issues I think are nice to talk about too, kind of the social dimension.
Yeah, it's actually kind of interesting. I think one of the biggest pushbacks for cochlear implants is actually among the deaf community, because the deaf community is very tight knit. They know each other, and they have their secret language and everything. And so it's almost like somebody's leaving the tribe. So yeah, maybe like maybe some of the biggest pushback, or a big part of the big pushback, might be from the people that are being left behind, something like this.
It's entirely possible. And, you've got a whole kind of culture that's grown up around people who have deafness or are deaf. This gets into, and who am I to say you have to have this cochlear implant so you can hear? Because you know what? They don't want to, and that's fine. But there's also kind of this, even just from society at large, is people will see something like a prosthetic limb, and it draws a lot of attention, which can make the person with the prosthetic limb feel uncomfortable sometimes. And I think that that's something we could just kind of make people aware of, and that people realize, it's a prosthetic arm, no big deal, right? It's nothing unusual about that. It's just something to help somebody out. And that's the kind of issue I think I encounter more than not. The other issue that I encounter a lot that gets very interesting is people start talking about augmentation. We've got, right now, currently our goal is just to really get people some vision to improve their quality of life. But then I always get the question of, could we give them X-ray vision, or could we give them infrared vision? And theoretically, yes, you could, just instead of using just a video camera that works with light, you could use, an infrared camera and let people have kind of augmented vision that they normally wouldn't have. And then you just got to ask the question, is that something people want? Is that something we should do? There's, some interesting ethical issues start creeping in with some of this technology.
Be like Geordi LaForge of Star Trek Next Generation, where you can see all the spectrum.
Yeah, and that's the classic example. I think, honestly, I don't think their brains are set up to process that much information, and so that could fall into the category of it's just overwhelming and people don't like it. But there's some interesting, fun things to talk about there.
Well, and if not that, then laser vision, like with Cyclops from X-Men.
Yeah, turn it around. No, I do not want to see this technology militarized, please. Can we just use it to help people? Okay. We just want to get... Yeah.
That's something we can both agree on.
Yeah, I don't want no lasers shooting out of people's eyes. So yeah, there's so much hope, and we're right on the cusp of it. I mean, it's one of those things, again, it just gets, it's almost like religious, and I get kind of zealous about this, I realize, but it's like getting blind people to see, it's like, wow, how cool would that be if it could really get something that really impacted and changed their lives and let them have, that human interaction that's so important. That's kind of the real motivating thing, I think.
Well, thank you so much, Dr. Bradley Gregor. This has been excellent. And maybe we'll hear you on the podcast again.
Well, my pleasure. Thanks for having me on, and I'd love to do it again in the future sometime.
Hey everyone, I hope you enjoyed this episode. This is actually our second time doing this episode. The first time we had some major connection issues, so we had to reschedule it. So it was kind of strange because I feel like the topic, the flow was completely different the first time. So it's kind of weird how these things go. Conversations are very fluid things, right? So if you change it one time, it's not going to be the same another time. But otherwise, I found this to be a very interesting episode about retinal implants and second sight and being able to give vision to blind people. So I really enjoyed this. Hopefully you were able to learn something as well. And yeah, some of you have written me like, oh, I'm using your podcast to narrow down my choices for who to go for a PhD or who to go for a postdoc. And yeah, so hopefully you were able to narrow down your search a little bit based on this. So until next time, this is the Neural Implant Podcast.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.